Go outside tonight. Find somewhere dark, away from the orange wash of street lamps, away from the glow of the city on the horizon. Drive out into the countryside if you have to. Lie down on the grass, fold your arms behind your head, and look up. On a clear night, away from any light pollution, you can see roughly 5,000 stars with the naked eye. 5,000 points of light scattered across the dome of the sky, each one a sun, a roaring furnace of nuclear fire, churning out energy on a scale that would reduce all of human industry to an irrelevance. Some of them are younger than our solar system. Some of them were burning before the Earth existed. A handful have been burning since the universe was young, back when the cosmos was a very different place and the first light was only just beginning to make its way through the primordial dark. It seems, on a night like that, as if the stars will always be there. The sky feels permanent, eternal. The kind of thing that will be there long after you and everyone you know is gone. Long after civilizations rise and fall. Long after the continents drift into new configurations. Long after the sun itself has swelled into a red giant and swallowed the earth whole. But here is the thing. The stars are not permanent. They are not eternal. They are, every single one of them, mortal. They are born, they live, and they die. And the universe is old enough, and the physics is clear enough, that we can calculate not only how they die, but when the very last one will die. When the final star in the universe will exhaust its fuel, cool to a cinder, and go dark. We know what that moment will look like. We know, roughly, when it will happen. And we know this is the part that should keep you up at night far more effectively than any ghost story. What the universe will look like in the immeasurable stretches of time that come after the last star, after the last light, in the deep, cold, almost inconceivably long darkness that will follow. This is not speculation. It is not science fiction. It is the considered conclusion of physicists and cosmologists who have taken the known laws of nature and followed them, without flinching, to their logical endpoint. The universe has a future. It is longer than you can imagine. And it is stranger than you would want to believe. The scale of now. Before we can understand where the universe is going, we need to appreciate where it is. We live, cosmologically speaking, in a golden age. Not in the sense that everything is going well. A cursory glance at the news will dispel that particular illusion. But in the astronomical sense that the universe, right now, is at the peak of its stellar activity. More stars are shining at this moment than at any other time in cosmic history, and more new stars are being born today than will be born at any comparable rate in the universe's future. This is a fact that takes a moment to absorb. We tend to think of the universe as something vast and ancient, something that has been around far longer than we can truly comprehend. And in human terms, that is entirely correct. The universe is approximately 13.8 billion years old. The Earth is 4.5 billion years old. Modern humans have existed for somewhere around 300,000 years. A blink of an eye in cosmic terms, a single page in a book that runs to millions of volumes. And yet, in the universe's own terms, it is still relatively young. The peak of star formation, the period during which the rate of new stars being born across the cosmos was at its absolute maximum, occurred somewhere between 10 and 11 billion years ago, when the universe was only 2 to 3 billion years old. Since then, the rate of star formation has been steadily declining. It has dropped by roughly a factor of 10 in the past 5 billion years. The universe is still making new stars, but it is doing so at a gradually dwindling pace, like a factory that is slowly running out of raw materials. Those raw materials are hydrogen and helium, the lightest elements, the fuel from which stars are built. They were forged in the first few minutes after the Big Bang, in a process called Big Bang nucleosynthesis, when the universe was hot and dense enough to fuse protons and neutrons into atomic nuclei. Everything heavier than helium, the carbon, the oxygen, the iron, the calcium in your bones and the iron in your blood, was made later inside stars and scattered into space when those stars died. But the total amount of hydrogen and helium in the universe is not infinite. Every star that forms, burns, and dies locks some of that original hydrogen away in the remnant it leaves behind. A white dwarf, a neutron star, a black hole. That hydrogen is no longer available to make new stars, and so, as the universe ages, the reservoir of raw stellar material shrinks. Star formation slows. Eventually, it stops. The last star will not be a dramatic event. There will be no explosion, no fanfare, no announcement. There will simply be a point, unimaginably far in the future, at which the last cloud of hydrogen collapses under its own gravity and ignites nuclear fusion in its core for the very last time. And that star, burning alone in a universe that has grown dark and cold around it, will be the final light. We know what kind of star it will be. We know roughly how long it will burn, and we know what kind of universe it will leave behind when it finally goes out. How stars live and die. To understand the last star, you first need to understand stars in general. And to understand stars, you need to understand one fundamental fact. A star is a battle. It is a contest between two forces played out over millions or billions of years, and the star exists only as long as the two forces remain in balance. On one side is gravity. A star is, at its most basic, a sphere of gas, mostly hydrogen with some helium, held together by its own gravitational attraction. Every atom in the star pulls on every other atom. The combined effect of this self-gravity is to compress the star inward, to squeeze it down, to try to make it smaller and ultimately collapse it into the smallest possible volume. On the other side is pressure. At the center of a star, the compression caused by gravity raises the temperature to extraordinary levels. In the case of our Sun, roughly 15 million degrees Celsius at the core. At those temperatures, hydrogen nuclei, single protons, are moving fast enough to overcome their mutual electromagnetic repulsion and come close enough together for the strong nuclear force to bind them into helium nuclei. This is nuclear fusion, and it releases energy. That energy creates pressure, an outward push that counteracts the inward pull of gravity. As long as fusion continues, the star is stable. The inward pull of gravity is exactly balanced by the outward push of fusion energy. The star holds its shape, burns steadily, and shines. But fusion consumes fuel. Every fusion reaction converts hydrogen into helium. The longer a star burns, the more of its hydrogen is used up, the more helium accumulates in its core. Eventually, in the Sun's case, in roughly 5 billion years, the hydrogen in the core is exhausted. Fusion stops. Gravity wins temporarily, and the core begins to collapse. What happens next depends on the star's mass. This is the crucial variable in stellar evolution. A star's mass determines how hot its core gets, how fast it burns its fuel, how long it lives, and ultimately how it dies. The most massive stars, those with 10, 20, 50 times the mass of the Sun, burn ferociously hot and fast. They exhaust their hydrogen in millions of years rather than billions. They then proceed through a sequence of further fusion stages, burning helium into carbon, carbon into neon, neon into oxygen, oxygen into silicon, and finally silicon into iron. Iron is the end of the road. Fusing iron absorbs energy rather than releasing it. The outward pressure vanishes. Gravity wins absolutely. The core collapses in less than a second, the outer layers rebound in a catastrophic explosion, and the star ends its life as a supernova, briefly outshining the entire galaxy that contains it, leaving behind either a neutron star or a black hole. Stars of intermediate mass, those between roughly 8.5 times the mass of the Sun, have a different death. They exhaust their hydrogen, expand into red giants, fuse helium into carbon and oxygen in their cores, and then lose their outer layers in a more gentle process, puffing them out into beautiful shells of glowing gas called planetary nebulae. The naked core that remains, a dense, hot ball of carbon and oxygen roughly the size of the Earth, is a white dwarf. It no longer fuses anything. It simply radiates the heat it has accumulated, cooling slowly over billions of years. And then there are the smallest stars, the red dwarfs, the little ones. Red dwarfs are the most common type of star in the universe. They are also the most overlooked. If you go outside tonight and look at the sky, you will not see a single one with the naked eye. They are too dim, too cool, too faint to register without a telescope. The stars that dominate the night sky, Sirius, Betelgeuse, Rigel, the brilliant blue-white giants that blaze across the winter sky, are spectacular but unrepresentative. They are the exceptions, the outliers, the showy celebrities of the stellar world. The quiet majority are red dwarfs. They account for roughly 70 to 80% of all the stars in the Milky Way. The nearest star to our Sun, Proxima Centauri, a mere 4.2 light-years away, is a red dwarf. So is Barnard's star, the second nearest. So are the vast majority of the stars you cannot see. Red dwarfs are small. The largest of them are about half the mass of the Sun. The smallest, the boundary between a red dwarf and a brown dwarf, a body too small to sustain hydrogen fusion, are around 8% of a solar mass. They are cool by stellar standards, with surface temperatures between 2,000 and 4,000 degrees Celsius, compared to the Sun's roughly 5,500. They glow red and orange rather than the white-yellow of the Sun, and they burn with extraordinary patience. The reason is that red dwarfs are, unlike the Sun, fully convective. In the Sun, the core where fusion occurs is surrounded by a radiative zone, a region through which energy moves outward purely by radiation, not by any bulk motion of the plasma. Above this is a convective zone where hot plasma wells upward, releases its energy, cools and sinks again, like the circulation in a boiling pot. This structure means that the hydrogen in the Sun's outer layers does not mix down into the core. The Sun can only fuse the hydrogen that was in its core to begin with. The rest stays in the outer layers, inaccessible, and will eventually be puffed away as the Sun expands into a red giant. Red dwarfs are different. Because they are fully convective, the plasma circulates throughout the entire star. Fresh hydrogen from the outer layers is constantly being mixed down into the core. The star has access to virtually all of its hydrogen, not just the fraction in its core. It is, in effect, a much more efficient engine, one that squeezes every last drop of usable fuel from its tank before spluttering to a halt. The result is a lifespan of breathtaking length. A red dwarf with a mass of 1/10 of the Sun's mass will burn for approximately 10 trillion years. That is 10,000 billion years. Our universe is currently 13.8 billion years old. A 10th solar mass red dwarf has a lifetime roughly 700 times longer than the current age of the universe. It has barely started. The smallest red dwarfs, those hovering just above the fusion threshold, may burn for up to 100 trillion years. 100,000 billion years, a number so large that the mind simply refuses to process it as something real. It is not a number you can feel. It is a number you can only note and move on from, shaking your head slightly. These are the last stars, not the spectacular blue giants, not the sun-like yellow dwarfs, not the orange subgiants. The last stars to burn in the universe will be these quiet, dim, patient, overlooked red dwarfs, husbanding their fuel with extraordinary efficiency, outlasting everything else by margins that make everything else look brief. A tour of the stelliferous era. Astronomers who study the long-term future of the universe have given names to the different eras of cosmic time, epochs defined not by years but by orders of magnitude, each one dwarfing the previous. The era we are currently in is called the stelliferous era. The word comes from the Latin for star-bearing. It is the age of stars. It began roughly 100 million years after the Big Bang, when the first stars ignited, and it will end. By the reckoning of physicists Fred Adams and Greg Laughlin, who wrote the foundational account of the universe's long-term future in their 1999 book, The 5 Ages of the Universe, somewhere around 100 trillion years from now. 100 trillion years. That number requires context. The age of the universe is 13.8 billion years, which we can write as roughly 10 to the power of 10 years. The stelliferous era ends at around 10 to the power of 14 years. 100 trillion. So we are currently, in logarithmic terms, somewhere around the 40th percent mark of the stelliferous era. Cosmologically, we are not in the twilight of the age of stars. We are in its afternoon. But the afternoon is ticking toward evening. Right now, the Milky Way contains somewhere between 200 billion and 400 billion stars. New ones are still forming at a rate of roughly 1 to 3 solar masses per year. Not as fast as the cosmic peak of star formation billions of years ago, but enough to keep things interesting. Our galaxy is a moderately busy place, with stellar nurseries in its spiral arms producing new suns at a steady, if unspectacular, clip. Over the coming billions of years, however, this rate will continue to decline. The giant molecular clouds, the vast cold reservoirs of gas from which stars are born, will gradually be depleted. Each star that forms draws hydrogen from the available supply. Each star that dies locks some fraction of that hydrogen away in the compact remnant it leaves behind. The supply is finite. The drawdown is relentless. Within a few trillion years, still within the stelliferous era, but deep into its twilight, the formation of sun-like stars will have essentially ceased. The only new stars being born will be the smallest ones, the red dwarfs, the marginal cases, the stars that form from the last thin dregs of available hydrogen. And one by one, over the following tens of trillions of years, the larger stars that formed earlier will exhaust their fuel and die. The blue giants will go first. They are already gone on any human timescale, burning for only millions of years before exploding. Then the white and yellow stars, lasting billions of years. Then the orange subgiants, until finally only the red dwarfs remain, scattered across a universe that has gone dark and quiet around them, burning on with the steady, unhurried patience of things that have nowhere to be. And eventually, the last of them will go out. The death of the last star. What will the death of the last star actually look like? When a red dwarf exhausts the last of its hydrogen, when the final fusion reactions sputter and die in its core, it will not explode. It will not expand into a red giant. It will not produce a planetary nebula, no beautiful shell of glowing gas drifting outward into the dark. It will simply fade. Without the energy source of nuclear fusion to maintain its pressure against gravity, the star will slowly contract. As it contracts, the gravitational energy released will heat the remaining plasma, and the star will briefly become hotter and bluer. A strange final flourish, a last gasp of warmth before the surface temperature begins the long decline. The star will cool over billions more years, fading from red to infrared to invisible, until it becomes what astronomers call a black dwarf. A black dwarf is simply a white dwarf that has cooled to the point where it no longer emits any visible light at all. It is a dark, cold, inert sphere of carbon and oxygen, roughly the size of the Earth, but with roughly the mass of the Sun, drifting alone and invisible in the empty dark. Here is an important detail about black dwarfs that is worth pausing on. In the current universe, no black dwarfs yet exist. Not one. The universe is not old enough. The oldest white dwarfs, the remnants of the first generation of stars to die, have been cooling for billions of years, and they have not yet cooled to the point of becoming black dwarfs. The cooling process takes longer than the current age of the universe. So the black dwarf is not merely a theoretical construct. It is a real object that will exist in the future, but simply has not had time to form yet. In the very far future, after the last red dwarf goes dark, the universe will contain enormous numbers of these cold, invisible remnants, white dwarfs still cooling toward black. Neutron stars, the dense remnants of stellar explosions, also slowly radiating their heat. Black holes, lurking at the centers of former galaxies and scattered throughout space wherever massive stars once died. And out among all of them, vast quantities of brown dwarfs, bodies too small to ever achieve nuclear fusion, failed stars, and rogue planets flung from their former solar systems by gravitational interactions, drifting dark and solitary through the void. The universe after the last star will not be empty. It will be full of things, but those things will be cold, dark, and silent. This is the era that comes next. The degenerate era. After the stelliferous era ends, after the last star burns out, somewhere around 100 trillion years from now, comes what Adams and Laughlin called the degenerate era. It is named for the physical state of the objects that populate it. White dwarfs, neutron stars, and the cooling remnants of red dwarfs are all composed of matter in what physicists call a degenerate state. In ordinary matter, in the atoms of your body or the gas of a star, electrons occupy a range of energy levels and can move relatively freely. But in the degenerate matter, the electrons are packed so tightly together that quantum mechanical effects take over. The Pauli exclusion principle, a fundamental rule of quantum mechanics stating that no two electrons can occupy exactly the same quantum state, means that the electrons are forced into higher and higher energy states as the density increases. The resulting pressure, degeneracy pressure, is what holds white dwarfs and neutron stars up against gravity. It is not thermal pressure, not the pressure of hot gas. It is a quantum mechanical effect, a consequence of the deep structure of matter. In the degenerate era, these objects will cool and darken. Brown dwarfs will drift in the void. Rogue planets will travel their solitary paths. Neutron stars will cool from their initial temperatures of millions of degrees to near absolute zero, over time scales that stretch the imagination. But something else will be happening during the degenerate era that is worth dwelling on. The proton, one of the fundamental constituents of ordinary matter, the particle that makes up the core of every hydrogen atom in every star that ever shone, may not be stable forever. Most of our intuitions about matter assume that protons are permanent. Knock out the electrons from an atom and the nucleus remains. Strip away the nuclear forces and the protons still exist. They seem indestructible. But certain extensions of the standard model of particle physics, particularly the grand unified theories or GUTs, which attempt to merge the strong, weak, and electromagnetic forces into a single framework, predict that protons should eventually decay, not quickly, not on any time scale remotely relevant to everyday life. The predicted half-life of the proton in the most widely studied GUT models is somewhere around 10 to the power of 36 years. That is 1,000,000 trillion years. It is a number so vast that every star that has ever shone, every galaxy that has ever formed, every black hole that has ever swallowed a solar system represents not even a single tick of the clock that measures proton decay. We have searched for proton decay with sensitive underground detectors and have not seen it. This has ruled out the simplest GUT models, pushing the proton lifetime above 10 to the 33 years. But longer-lived proton decay remains possible, and if it occurs, it will have a profound effect on the degenerate era. Over time scales of 10 to the 37 years or so, even if the proton is quite long-lived, the remaining white dwarfs and neutron stars, the black dwarfs and cooling remnants of the degenerate era, will slowly dissolve. Their constituent protons will decay one by one, converting their mass into lighter particles and ultimately into energy. The cold, dark remnants of dead stars will quietly evaporate, radiating a faint glow as they go and disappear. If proton decay does occur, nothing made of ordinary matter will survive into the far future of the universe. Everything that stars were made of, everything that planets were made of, everything that life was made of, gone. The expanding dark. While all of this is happening, while stars are exhausting their fuel and dying, while their remnants are cooling and darkening, while protons may or may not be slowly decaying, something else is going on at the largest scales. The universe is expanding, and the expansion is accelerating. This was discovered in 1998 by two independent teams of astronomers, one led by Saul Perlmutter, the other by Brian Schmidt and Adam Rees, who were studying Type 1a supernovae, the explosions of white dwarfs that briefly outshine their entire host galaxies. These supernovae can be used as what astronomers call standard candles. Their intrinsic brightness is known well enough that by measuring how bright they appear from Earth, you can determine how far away they are. The teams were measuring the distances to very distant supernovae to track how the universe's expansion had changed over time. They expected to find that the expansion was slowing down. Gravity, acting on all the matter in the universe, should be putting the brakes on. The universe should be coasting, decelerating, perhaps eventually collapsing back on itself. Instead, they found that the expansion was speeding up. The distant supernovae were dimmer than expected. They were farther away than a decelerating expansion would have placed them. Something was pushing the universe apart, overcoming gravity, making the expansion not slow down but accelerate. That something is what physicists now call dark energy. Its nature is unknown. It may be a property of space itself, a cosmological constant, a fixed energy density that every cubic meter of space carries regardless of what else is in it. Or it may be something else entirely, something that changes with time in ways we do not yet understand. What we do know is that dark energy currently constitutes roughly 68% of the total energy content of the universe. It is the dominant component of the cosmos by a wide margin, and its effect is to drive the accelerating expansion that will, in the very long run, have an extraordinary consequence. Galaxies that are currently gravitationally bound to each other, galaxies in clusters and superclusters, will remain bound. Gravity can hold them together against the expansion. But isolated galaxies, those without close gravitational neighbors, will find that the expansion of space gradually carries them beyond what cosmologists call the cosmic horizon. Beyond this distance, the recession speed exceeds the speed of light, and no signal can ever reach us from there. Those galaxies will vanish from our observable universe forever. This is already happening. The vast majority of the roughly 2 trillion galaxies in the observable universe are already receding from us faster than light. They are visible now only because the light we see from them was emitted long ago, before the expansion had pushed them beyond the horizon. The light currently leaving those galaxies will never reach us. In roughly 2 trillion years, even the nearest galaxies outside our local group, the gravitationally bound collection of galaxies that includes the Milky Way and Andromeda, will have crossed the horizon. The night sky, viewed from a future civilization in a far future Milky Way, will be utterly dark beyond our own galaxy and its immediate neighbors. No other galaxies will be visible. The evidence for the Big Bang, for the expanding universe, for the vast cosmic web of structure that we can see today, all of it will have been swept beyond the horizon, invisible forever. A civilization that evolved at that point in cosmic time with no fossil record of the cosmological evidence we enjoy today would have no way of knowing that the universe was once full of light. The black hole era. Beyond the degenerate era, beyond the evaporation of protons and the extinction of all ordinary matter, comes the black hole era. Black holes are, in a profound sense, the most durable objects the universe produces. They are regions of space-time so severely curved by gravity that nothing, not matter, not energy, not light, can escape from within them once it has crossed the event horizon. They form from the deaths of the most massive stars and from the mergers of dense stellar remnants, and perhaps in other ways too. The supermassive black holes at the centers of galaxies, objects with masses millions or billions of times the mass of the Sun, were already enormous in the early universe and have been growing ever since. In the black hole era, these objects will dominate a universe that contains almost nothing else. The stars are gone. The stellar remnants have decayed. The galaxies have been dispersed by the expansion of space. What remains is a sparse population of black holes of various sizes drifting through a cold and dark cosmos. But black holes, as Stephen Hawking showed in 1974, are not truly black. They radiate. The mechanism is subtle and rests on the quantum nature of the vacuum. Near the event horizon of a black hole, the intense curvature of space-time affects the quantum fields that permeate all of space. In ordinary flat space-time, the vacuum has a definite state, a ground state devoid of particles. But in the curved space-time near an event horizon, different observers disagree about what constitutes the vacuum state. An observer falling into the black hole sees the vacuum as empty. A distant observer sees the black hole emitting a faint thermal glow, Hawking radiation. The energy for this radiation comes from the black hole itself. As it radiates, it loses mass. The more mass it loses, the smaller it becomes. The smaller it becomes, the hotter it gets. The temperature of Hawking radiation is inversely proportional to the black hole's mass. A small black hole is hotter than a large one. So as a black hole radiates and shrinks, it radiates faster and faster in a runaway process that ends in a final explosive burst of energy as the last fragments of mass are converted to radiation. For a stellar mass black hole, the remnant of a star 10 or 20 times the mass of the Sun, the evaporation time is roughly 10 to the power of 67 years. For the supermassive black holes at the centers of galaxies with masses billions of times larger, the evaporation time stretches to around 10 to the power of 93 years. These are not numbers that invite intuitive comparison. 10 to the 93 is not a large number in the way that a million is a large number, or even in the way that the number of atoms in the observable universe, around 10 to the 80, is a large number. It is a number that exists in a different category of magnitude altogether, but it is finite. Even the largest black holes in the universe will eventually evaporate. Every one of them, given enough time, and the universe has more than enough time. There is no black hole so massive that Hawking radiation will not, in the end, reduce it to nothing. And when the last black hole evaporates, the black hole era will be over. The long silence. What comes after the last black hole? This is the question that sits at the very end of the known physics of cosmic time. It is the question that Adams and Laughlin call the dark era, and it is, in some sense, the most interesting of all. Because the answer is not nothing. The answer is a universe that is not empty, but in which almost nothing happens. After the last black hole evaporates, the universe will contain only the products of that evaporation and the long decay of earlier eras. Photons of various wavelengths, stretched to extraordinary lengths by the continued expansion of space. Electrons and positrons and neutrinos, the lightest particles, drifting in a cosmos so cold and so expanded that the average distance between any two particles will be unimaginably vast. The temperature of the universe, as measured by the cosmic microwave background radiation, the thermal afterglow of the Big Bang, will have dropped to a fraction so close to absolute zero as to be indistinguishable from it. The universe will be, for all practical purposes, at thermal equilibrium. This is the heat death, the state of maximum entropy predicted by the second law of thermodynamics, in which the universe has run down to a uniform temperature and no further useful work can be done. No temperature gradients, no concentration of energy, no potential for organized complexity. Just a cold, dark, vastly expanded void with the faintest possible sprinkling of the lightest possible particles. This is how the universe ends. Not with a bang, not with a crunch, with a whisper spread across time scales so enormous that the entire history of stellar evolution from the first star to the last, 100 trillion years, looks like a brief, brilliant moment of warmth and light. But here, the story takes one more strange turn. The quantum long shot. The dark era is not, technically speaking, a static equilibrium. It is, technically speaking, a quantum state, and quantum states can fluctuate. The same principle that gives rise to Hawking radiation, the quantum mechanical behavior of the vacuum, means that even in the most quiescent, dead, empty corner of a maximally expanded universe, quantum fluctuations will continue to occur. Virtual particles will continue to pop in and out of existence. The vacuum will continue to be not quite nothing, and over time scales that make even the black hole era look brief, something remarkable, or rather, something deeply improbable, will happen. Purely by chance, quantum fluctuations will occasionally produce small arrangements of matter with slightly lower entropy than the surrounding void. These fluctuations are fantastically rare. The probability of any given fluctuation producing a structure of any significant complexity is vanishingly small. But the universe in the dark era has something that more than compensates for vanishingly small probability. It has essentially infinite time. The philosopher Ludwig Boltzmann first grappled with this idea in the 19th century. If you wait long enough, and by long enough, Boltzmann meant time scales almost beyond any mathematical expression. A fluctuation in an equilibrium system could spontaneously produce any configuration of matter, no matter how ordered or complex. In principle, an entire planet could coalesce from the random jostling of particles. In principle, a galaxy could flicker briefly into existence from a purely random quantum fluctuation. And in principle, though this is the strangest of all, a single conscious mind could spontaneously assemble itself from a random fluctuation in the quantum vacuum. A brain with no body and no history, containing a set of memories and the experience of being alive, persisting for long enough to have a single thought before dissolving back into the void. Physicists call this hypothetical entity a Boltzmann brain. The probability of a Boltzmann brain forming is essentially zero for any practical purpose. But in a universe of infinite duration, with essentially infinite time available, it may happen. Over time scales of perhaps 10 to the power of 10 to the power of 50 years, a number so recursive it barely qualifies as a number at all, random quantum fluctuations might briefly and discontinuously produce a moment of experience in an otherwise dead universe. Whether this is comforting or not is a matter of personal philosophy. What the last star means. We have traveled a long way from the hillside on a clear night, staring up at 5,000 stars. Let us take stock of the journey. In roughly 5 billion years, the sun will exhaust its hydrogen, expand into a red giant, swallow the inner planets, shed its outer layers, and leave behind a cooling white dwarf. The Earth, if it survives the expansion phase, will be a charred and lifeless rock orbiting at a greater distance than it does now, cold and dark in the absence of the sun's warmth. In roughly 100 billion years, the Andromeda Galaxy will have merged with the Milky Way in a slow-motion collision that began several billion years ago and will play out over billions more. The collision will not be violent in any everyday sense. Galaxies are mostly empty space, and individual stars will almost never physically collide. But it will scramble the structure of both galaxies, sending stars on new orbits, disrupting the spiral arms, and ultimately producing a single, large elliptical galaxy. Astronomers sometimes call this future merged galaxy Milkomeda. In roughly 1 trillion years, the supply of gas available for new star formation in our galaxy will have been largely exhausted. The last sun-like stars will have died. Only the dimmest red dwarfs will still be burning, scattered through a galaxy that has grown dark and quiet. In roughly 100 trillion years, the last red dwarf will exhaust its fuel and cool to a black dwarf. The stelliferous era will end. The universe will then contain only the cold remnants of dead stars, drifting brown dwarfs and rogue planets, the occasional neutron star, and the patient black holes. If proton decay occurs on the predicted timescales, even the remnants of ordinary matter will eventually dissolve. The black hole era will last for timescales utterly beyond human conception, ending only when the last supermassive black hole radiates away the final fraction of its mass in a burst of Hawking radiation. And then, the dark era. The cold, the silence, the almost nothing. This is the fate of the universe as currently understood by cosmology. It is, on first encounter, a deeply melancholy picture. The stars are beautiful. They have warmed our planet, powered our biosphere, and made possible everything that we are. The idea that they will all eventually go dark, that the universe will grow cold and empty, that even the most durable remnants will eventually decay and dissolve, can feel like a kind of cosmic injustice. But perhaps it is worth reframing it. The rarity of now. Consider what it means to exist in the stelliferous era. We live in the brief, brilliant window of cosmic history when stars burn, when planets form around them, when chemistry is driven by starlight and liquid water and the energy gradients that make life possible, when the universe is warm enough, active enough, full enough of available energy to support the extraordinary, improbable phenomenon of organized complexity, of molecules that replicate, of cells that metabolize, of nervous systems that perceive, of minds that wonder. This window is finite. We know that now. The stars will go out, the warmth will end, the long cold will come. But the window is also enormous. The stelliferous era will last roughly 100 trillion years. We are currently 13 or 14 billion years into it. We are not at the end. We are, by cosmic standards, near the beginning. The stars have barely got started. The era in which life is cosmically possible, the era of starlight and energy and warmth, extends far ahead of us into the future for timescales our minds cannot genuinely process. The physicist Freeman Dyson once argued that life need not end with the stars. He proposed that intelligent life, if it survives long enough to encounter the challenges of a cooling universe, might be able to adapt, to slow its own metabolism, hibernating through long cold epochs and briefly waking for bursts of activity, to migrate toward the remaining energy sources, however faint, to find ways to maintain the structures of thought and experience even as the universe cools around it. Dyson was not predicting that this would happen. He was exploring the question of whether the laws of physics permit it. His conclusion, arrived at in 1979 with characteristic rigor and imagination, was that the laws of physics do not obviously prohibit life from persisting indefinitely into the future, even in an increasingly cold and empty universe. Whether any life actually manages this, whether any intelligence anywhere in the universe survives to witness the death of the last star, or the evaporation of the last black hole, or the quantum silence of the dark era, we cannot know. But the possibility is there. The physics does not forbid it. And there is something extraordinary in that. What we do not know, for all the confidence with which we can outline the broad arc of the universe's future, it is worth being honest about the uncertainties. We do not know whether the dark energy that is currently driving the accelerating expansion of the universe will remain constant. If it remains as a cosmological constant, if the energy density of space stays fixed, then the universe will expand forever, cooling asymptotically toward absolute zero. And the picture we have described is broadly correct. But if dark energy grows stronger with time, the universe's expansion could accelerate to the point where the force tears galaxies apart, then solar systems, then planets, then atoms. A scenario called the Big Rip, in which the universe ends not with a cold whisper, but with the violent shredding of all structure at every scale. We do not know which of these futures is correct. We do not even have a theoretical understanding of what dark energy is. We do not know whether protons decay. The standard model of particle physics, in its current form, predicts that protons are stable. Their lifetime within the standard model is essentially infinite. The proton decay we discussed earlier is predicted by extensions of the standard model, grand unified theories, that have not been confirmed by experiment. The simplest GUT models have been ruled out by the non-observation of proton decay in underground detectors. More complex models with longer proton lifetimes remain viable but unconfirmed. Whether ordinary matter will eventually decay, or whether the black dwarfs and neutron stars of the degenerate era will persist indefinitely, depends on an answer we do not yet have. We do not know whether Hawking radiation is real. This one is striking enough to deserve a moment's pause. Hawking's calculation of black hole radiation is widely regarded as one of the most beautiful and important results in theoretical physics. But it has never been directly confirmed by observation. The temperature of Hawking radiation from a stellar mass black hole is so extraordinarily cold, a fraction of a millionth of a degree above absolute zero, that it is completely undetectable against the warmer background of the cosmic microwave background radiation. We have no observational evidence that black holes evaporate. The theoretical argument is compelling, and most physicists accept it, but it has not been tested. If Hawking radiation turns out not to exist, If some aspect of the calculation is subtly wrong in a way that has not yet been identified, then black holes might not evaporate. They might be genuinely eternal. The black hole era might last forever. The universe's future would be the permanent, frozen coexistence of a cold vacuum with an unchanging population of black holes. We do not know. And finally, we do not know whether our universe is the only one. If the multiverse hypothesis is correct, if our observable universe is one of an enormous or infinite number of separate universes, each with its own physical laws and constants, then the fate of our particular universe may be less cosmically significant than it appears. There may be other universes in which the laws of physics are different, in which stars burn differently, in which the future unfolds along entirely different lines. Our universe's long, cold death might be just one outcome among infinitely many. Whether this is comforting is, again, a matter of philosophy. The last light. Go outside tonight. This time, do not just lie on the grass and count the stars. Look at them differently. Look at them knowing what you now know. Every star you can see, every point of light in that dark dome above you, is a nuclear furnace burning hydrogen into helium, pouring energy into the universe at a rate that staggers the imagination, maintaining the conditions for warmth and chemistry and life on the planets that orbit it. Each one is temporary. Each one is drawing down a finite reservoir of fuel that will, eventually, run to nothing. And yet look at how many there are. The 5,000 stars visible to the naked eye represent only the nearest fraction of the 200 to 400 billion stars in our galaxy alone. And our galaxy is one of roughly 2 trillion galaxies in the observable universe. The total number of stars currently burning across the cosmos is somewhere around 10 to the power of 24. A million trillion. That is more stars than there are grains of sand on all the beaches of all the oceans on Earth. For roughly 100 trillion years. For a span of time that makes the current age of the universe look like the opening sentence of a very long book. The universe will continue to be a place where stars burn, where light exists, where chemistry and energy gradients and the possibility of life endure. The last star will be a red dwarf, dim, quiet, patient beyond all reckoning. It will burn alone in a universe that has grown dark around it, the sole surviving light in the sky of any world still orbiting it, if any such world remains. It will have no stellar companions. The galaxies that once surrounded it will have long since dissolved and scattered. It will burn in a darkness almost total, a tiny flame of hydrogen fusion at the end of an incomprehensibly long age of light. And when it finally cools, when the last fusion reaction sputters in its core and the remaining warmth slowly radiates away into the dark, the stelliferous era will be over. The age of stars will have ended, and the long, deep, almost endless darkness of the universe's future will begin in earnest. This is not a cause for despair. It is a cause for attention. We are here now. You are here now. In the middle of the stelliferous era, in the warmth of a star that has 5 billion years left to burn, on a planet that has spent 4.5 billion years growing complex and rich and strange, in a moment of cosmic history that is warm and bright and full of light. The light is not permanent, but it is here. Look up. The stars are burning. You've been watching the entire history of the universe. Don't forget to like and subscribe, and leave a comment to tell us what you think. Thanks for watching, and we'll see you next time.